Hi everyone, my name is Mike Gok. Today I'm going to talk about mechanical copier, a pantograph. What is a pantograph? Here is an example. A pantograph is basically a mechanical linkage in which a point such as E shown in this animation is a driving point. C is a follower that traces the same image that E is tracing, which is a triangle in this example. As you can see, the triangle at C is smaller than the triangle at E, and there are certain relationships in this. This example is taken from YouTube. As you can see, ABCD is a parallelogram. OCE remains a straight line throughout the motion. O is a point that is immobile. And the scale factor OE to OC is basically the size factor of triangle at E relative to C. Let's take a look at a pantograph used by a carpenter to carve wood.
This video is about carving 3D indented letters with my router pantograph. My pantograph not only controls the position of the router but also its depth, which allows me to carve these profile letters that actually have a variable depth of cut along the whole letters. The way the pantograph works is I have a conical follower which follows the grooves in the template and a V-bit that is the same shape as my conical follower. Now, if I have a wider gap in my template, as you can see here, then the conical follower can dip deeper into that template, which will tilt the whole pantograph forward, and that in turn will drive the V-shaped cutter deeper into my stock, which will make for a deeper, wider cut.
Let's take a look at another pantograph. Here we have point E driving point F. Both of them trace similar triangles at different sizes. Again, this example is taken from YouTube. As you can see, in this example, we have OBCD being parallelogram. OFE stays in a straight line throughout the motion. We have an immobile point O, and then the scale OE relative to OF is the size ratio of triangle at F relative to that traced by E. Let's take a look at the motion of the two pantographs. They both serve the same purpose, and they have almost the same scale factor. In other words, there could be more than one design to a pantograph that serve the same function. Let's take a look at the last pantograph example today. Here we have what we call an inverted pantograph. Let's take a look at the motion. As you can see, as point E is driven to trace a triangle, point C is tracing a smaller yet inverted triangle. So here, another example taken from YouTube, we observe that OABD is a parallelogram. COE remains a straight line like in the last two examples. We have an immobile point O and then a scale factor OC relative to OF, which is the size of the triangle traced by point C relative to point E. Are you not amazed by the principles of a pantograph? Do you know that you can make one at home? Let's try that. To make a pantograph prototype, you need a cardboard. You may use plastic corrugated board if you have some, and I have here some left over. I only need an area spanning 200mm in length and 75mm in width. I will then cut these areas into 4 strips as shown. Other materials you need are a pair of scissors, a ruler, a pencil, a color pen, a piece of straw, some clear tape, a thumbtack, and a hole puncher. All these materials can be easily found at your local stores or Mr. DIY. Now let's get into action. First, mark the areas that we need to make 4 strips of materials as shown in the last slides. The 4 pieces are 2 longer pieces with length of 200mm and width of 25mm, and 2 shorter pieces of length 100mm each. and with the same width of 25 millimeter. Alright, we have them. Let's cut them into the strips that we want. Now is the time to mark the holes. All the holes are 80 millimeters apart. Here I use eyeballing to estimate the center position of the strip. You may want to use a ruler to help you. I like to use crosses to help me mark the position better. As you can see, the first hole on the long strip begins at a position of 10 millimeters from the edge. Because the subsequent holes are positioned 80 millimeters apart, the last hole on the long strip will end up at a position of 30 millimeters from the other edge. Now that the holes are ready, it is punching time. I like to label the joints of the pantograph, and I use the letters O, A, B, C, D, E as shown in this picture at the top left corner. This is how the pantograph looks like finally. But how are we going to join the pieces we made? Well, I'm going to use straws to replace screws. We are going to need 3 pieces of straw, each 20 mm in length. Now for each short piece of straw you just cut, you are going to make 4 snippet cuts at its end. Since the straw that I have has 4 lines on its side, I'm going to use the lines to guide me. Now after the cut, fold the cuts outwards so that you form petals as you can see here. In the next step, you are going to align the holes at joint A, B, and D. You are going to place the straw pieces into those joints with the petals facing you. You have to do this one at a time. When you have inserted the first straw at the joint, you are going to flip to the back and then cut 4 lines as you done before and form a petal at the other side. Use clear tape to secure each straw piece at its joint location. Let's push the thumbtack through location C. Voila, we have the pantograph. Now insert the pencil at joint E and then insert the color pen at joint O. Your pantograph is now ready for action. Here I have cut a square out of a piece of cardboard and use it to guide my pencil. I'm going to trace the square using the pencil. With the pencil and the color pen in their positions, let's see what happened. Well, you can see the color pen traces a square like the pencil. That's why the pantograph is called a mechanical copier. Instead of a square, I have made a mountain shape for tracing. Let's see what happened. Did you see that? The mountain shape traced by the color pen is inverted. What if I position the pencil and the pen at 10 mm away from the bottom edge? Let's see what will happen. You see that the mountain shape traced by the color pen is distorted. How does that happen? The distortion happened because the points O, C, E no longer lie on a straight path. Instead of changing the length of each piece or make holes at different locations, are there any easier ways to investigate the changes on the pantograph? The answer is yes, we can make a digital twin. Next, I'm going to show you how to make a digital twin on AutoCAD Inventor. Let's start by drawing out the outlines of the strips and then extrude them. Then we punch holes at desired locations. I'm going to assign different colors for the long strips and the short strips. Now that the long strips are done, let's move on to the short strips. In this digital twin, I'm going to add holes at location C where I have my thumbtack. Last but not least, we are going to make the 5 pins. Let's make an assembly of all the 5 pins and the 4 strips. First, pull in all the necessary components into the assembly. Then rotate and move the components to their approximate locations to ease your assembly. It is time to constrain the pins onto the hole, and when they are done, you can hear a snap sound. Our digital twin is done. Let's move it around to see the motions. You can see the pantograph moving around because none of the pins was nailed down. Let's pin down the joint at C and see what happens. This is exactly how our pantograph moves. Let's do a quick experiment by grounding pin O instead of C and see what happens. Is this what you have expected? This is an example of a mechanical project utilizing linkages as in the pantograph. What you see here is a sub-assembly of a hand exoskeleton, which is used to rehabilitate patients with hand injuries. You can add traces to the pins or joints to see the motions clearer. This was my final year project student who designed the hand exoskeleton. She was using the NeuroSky MindWave brain-computer interface to control the motion of the hand exoskeleton. We have come to the end of today's 3H show. I hope you enjoy it. Come learn with us.